Well, thank you all for joining us today. We're going to talk about and then answer questions about a revolution that's happened over the time that this festival has been running. Over its lifetime, there have been three parallel revolutions that really play a critical role in our understanding of the possibilities for life elsewhere in the universe. One of them is in biology, where we've revolutionized our understanding of how life can survive in extreme environments. Another is in our understanding of the ubiquity of water in the solar system and the possible sites for life to form and thrive elsewhere in our own solar system. And then finally, our understanding of the existence of other planets around other stars in great profusion and in great variety is changing our picture of where to go. And as we refine the techniques that have brought about this revolution, we expect great discoveries from the future, going from the rather conjectural picture you see here to a more realistic picture of what's going on. You'll see in the course of this a number of slides, most of which are real. There are a few ones that are artist visions, but it's really quite an exciting world. And I want to introduce our panel here who will spend a few minutes each describing their areas of expertise and how they play into this whole thing. And then we'll open it up for questions and discussion. So first to my right is David Hoffman, who's a professor of molecular biosciences and expert on extreme life in extreme environments. Cyril Grima is a research scientist in the Institute for Geophysics, an expert on ice reservoirs on Earth and on other planets in our solar system, particularly interested in the prospects for life on Europa, which he'll talk about a bit. And then our assistant director of our McDonald Observatory, Anita Cochran, who is an expert on comets, which play a critical role in this whole process, both in our own solar system and probably in other solar systems as well. And Taft Armandroff, who's the director of McDonald Observatory, who will talk a bit about the technological revolution that will lead to our ability to actually detect the spectral signatures of bioactivity in other planetary systems. David, you want to start and tell a little bit about your work?
Well, I guess my expertise would be in, microbe metabolism on Earth, because we don't have any microbes yet around Earth 2 or extrasolar planets. I think I'm really excited about hopefully seeing in the very near future would be evidence of compositions of atmospheres of other planets that would provide us with information about what type of metabolism is happening on these extrasolar planets. For example, Earth's atmosphere's composition has just changed, gone through many compositional changes in the last 3.5 billion years, and much of Earth's atmosphere's composition is actually a product of the life that's happening on Earth at that given time. So, for example, a lot of us are aware that all the oxygen we currently have in Earth's atmosphere is a product of photosynthesis. But for the first third of Earth's history, there was no photosynthesis, but there was methane, which was a product of methanogenesis, methanogens, microbes. But there's been these various cycles. And I'm just really excited that hopefully in the not too many years in the future, we'll actually get information about the composition of other atmospheres. And then people who are fascinated with metabolism, like I am, can start trying to piece together what's going on these planets. And another thing that is fascinating, in the last decade or so, we've gotten we've learned an enormous amount of how tough life is. For example, 15 years ago, I don't think we appreciated how microbes especially can survive in incredibly hostile conditions on Earth. I mean, like, not just heat, but in the maybe 5 to 7 kilometers below the surface of the Earth, living in essentially porous rock with almost no nutrients, with just the barest trace of nutrients. Life can live there, can live in those environments, and that really wasn't appreciated until relatively recently, which can make people like me a lot more optimistic about finding life, maybe even on our own solar system, living especially in the deep subsurface of Mars, Europa, Titan, Enceladus, that sort of thing, moons within our own solar system.
Great.
Yeah,
Cyril.
so I'm doing my researches, I'm specifically doing my researches on planetary cryosphere in the solar system, trying to characterize the cryosphere and the planetary in the solar system, to quantify the cryospheres, how much water ice first you have on different planetary bodies. And this is done with different kind of remote sensing instruments on board spacecraft and orbiter first, but also some instruments on aircraft on Earth, because when I'm talking about planetary bodies, I include Earth. And we learn a lot about the possibilities for habitats in other worlds by looking at the Earth itself. And cryospheres in other worlds have been we've learned a lot since the past 10, 15 years about that, because we had some new instruments, especially on Mars, where we have found a lot of water ice that actually shape the landscape of Mars. And we know, for example, that on Mars there is lying at the surface a lot of glaciers and two polar caps. If you melt all of them, this would represent what we call a global equivalent layer, a layer of water that is 25 to 30 meters thick over the whole planet. But on Mars, the water is frozen so far. Or sometimes we can maybe detect some kind of liquid water, but this is very unstable and localized. But apart from that, there is other worlds on the solar system, and especially the icy moons of Jupiter and Saturn. On Jupiter, I'm especially talking about Europa, where we can see from outside that you have an entire crust of water ice. But because of the energy generated by the tidal forces between Jupiter and Europa, the base of this crust of H2O is liquid. And the ocean beneath this crust represents in volume twice the oceans of Earth. And there is a lot of other things we could discuss afterwards to tell about Europa and the potential for other water worlds, subterranean water world in the solar system and in the cryospheres, below the cryospheres.
So David and Cyril talked about looking for things that look like life today. And one of the problems, as David points out, is that the atmospheres that we see today are not the atmospheres that formed with the planets in the solar system. The planets we see today are not the planets that, as they formed, they've undergone a lot of change. They were formed out of much smaller particles. And the thing that's most akin to what formed our planets are the comets that we see today. And the comets are basically dirty snowballs. They're icy and dirty bodies. And they are responsible for being the building blocks of the planets, but they also are responsible for transporting materials from the outer part of the solar system where you can have ices and water and bringing it into the inner planets. So if you crash a comet into the Earth, you're going to bring a substantial quantity of water. Well, enough of those, and you certainly can start bringing in other types of atmospheres. So we study this to try to understand our solar system. But remember that our solar system is one example, and we started looking for planets around other solar systems, other stellar systems, assuming that planetary systems would look like ours. And in 1995, the first planet around a star other than our own, normal star other than our own, was found, and it didn't look anything like us. It had a Jupiter-sized body that was inside the orbit of Mercury. And since then, there's been thousands of planets found, and we haven't yet found the exact analog. So when we start talking about Earth 2.0, we have to not only understand what exists in our solar system, we have to try to be creative about what conditions, the very extreme conditions that David talked about, can allow for Earth and other things that would make it look like a true Earth 2.0.
I'd like to mention some of the amazing tools we have to study this fascinating problem. And just to give you some context, astronomers have been looking for planets beyond our own solar system since the scientific revolution, really. And it's only been within the last 20 years or so that we know of any planets that aren't the ones we all learned in elementary school and memorized the order, going out from the sun out to Pluto, which, as you all know, has been recharacterized as a dwarf planet. So it's taken amazing advances in technology to do this. Some of the same things that drive technology that have changed our world in other ways are having a profound impact on astronomy and our society's knowledge of the universe that we live in. And the University of Texas at Austin plays a role in this in two contexts. One of them is the McDonald Observatory that we operate, that's about 7 hours west of here in nice dark sky country. We have a wide range of telescopes and instruments there that help us study exoplanets. And then UT is a partner in the Giant Magellan Telescope that's being built in northern Chile. That'll be the largest telescope in the world when it comes online in 2022. And in both at McDonald and the Giant Magellan Telescope, we're working to optimize the technology to participate strongly in this exoplanet revolution and to push the frontiers forward. And essentially, we have three primary tools for doing this. One of them is really precise spectrographs that help us measure the wobble of stars as the planets orbit around them. So that helps tell us whether a star has planets and what the masses of the planets are. And it's been incredible, the number of stars and the frequency of planets that have been determined in this way. And the Giant Magellan Telescope will have this capability as well. We also take detailed spectra of stars at McDonald, and we plan to, at the Giant Magellan Telescope, to look for the signatures in the optical and infrared spectra of planets that are orbiting the stars. And then finally, we use a revolutionary technology called adaptive optics to image planets. So adaptive optics removes the blurring that's caused by the atmosphere. The atmosphere introduces distortions in the images. And by changing the shape of a relatively small mirror about this size very rapidly to counteract the effects of the atmosphere, we can have the telescope behave as if there weren't an atmosphere above us and make images that are of incredible sharpness, 10 times the sharpness of the Hubble Space Telescope, and that will allow us to directly image planets with the Magellan Telescope. And the Giant Magellan Telescope, once one can directly image planets and through these other techniques, we'll be studying the atmospheres of exoplanets. And that's really the holy grail for understanding this Earth 2.0 problem.
Thank you. So, David, can you tell me a little bit about what you might expect to see in an ocean on Europa if you could actually sample it? What would you find there?
Oh, gosh. We'd be looking for evidence of metabolism. Okay, so if you look for, say, evidence of metabolism on Earth in sparse environments, you'd be looking for things like the presence of methane, which is the waste product of a class of microbes called methanogens, which is a type of microbial metabolism which seems to be very well suited to extremely harsh environments. So methane would be a sign of life, or at least not an unequivocal identifier of life, but it'd be an indication there could be life there. So methane would be a really good trace, as opposed to, and in addition to things like more obvious things such as the presence of organic molecules, where you perhaps have an excess of one enantiomer over another, indicating they've been processed by an enzyme. It's that type of thing.
So, Cyril, when you're talking about our own solar system, most of what you talk about are moons. Do you think that because of this need to generate heat in other ways, that the prospects for finding life in other solar systems might rely on more around moons, around giant planets, with an analogy to Jupiter, rather than the planets themselves? Or is that an unrealistic expectation?
Well, that's true that to have life, so you need several ingredients, and one of them is to have energy, free energy, to start the metabolism process. And most on Earth, this energy is coming either from the sun, photosynthesis, or from volcanic activity at the hydrothermal vents in the ocean, for example. And this would be basically the energy we could expect on Europa. And the source of this energy on Europa was quite unexpected some decades ago, because it happened that Europa is orbiting Jupiter not in a perfect circular orbit, but it's a kind of ellipse. And because Europa is going fore and aft towards Jupiter, it generates this tidal hit inside. And this could be the source of some energy for life. You have also some other sources we can find in many planetary bodies, but which is, for example, the disintegration of the isotopes in the planets. All of those energy alone are sometimes not in. We think it's not enough to at least have life with complex individuals like us, but altogether, tidal hit from orbiting, this disintegration of isotopes, altogether is actually maybe a chance for life to initiate.
So Anita, you mentioned the bringing of water by the comets, but water alone is not enough to make life, and don't comets also bring other prebiotic molecules that might be important in this process?
Yeah, when we study comets, of course, we're limited by the fact that up until the European Space Agency's Rosetta mission, we hadn't had samples of the comet. So we didn't know a lot about the detailed chemistry. Water is the obvious thing that we did know about. We know that it's necessary to have liquid in a cell to have life. But there are other things, amino acids and things like that. We have now detected in cometary materials things that are very indicative of being precursors of life. And so it is certainly likely that comets have come to the Earth and have brought material. And how important they were, lysine, things like that, to starting life, we don't know yet. But certainly they must have contributed some.
So Taft, could you tell us a little bit more about the process of discovery that we expect to go through? I mean, we're not going to actually resolve the individual planets. We'll be able to separate them from the stars. But how does the instrumentation actually tell us what's there?
Yeah, astronomers don't really get to do experiments the way physicists do, so we have to watch very precisely to conduct our observations. So, yeah, Dan is quite correct. We will use these adaptive optics systems to form very high-resolution images of a star that'll allow the exoplanet and the star to be separated, and then we'll take a spectrum of the exoplanet with no contribution of light from the star. In effect, we'll be able to minimize the amount of starlight there and subtract it off. So we'll get a pure spectrum of an exoplanet in this one mode. In another mode, we can use the fact that a star eclipses the exoplanet, so that the orbit of the star would carry the planet back and forth, where you get the light reaching Earth, either star plus planet or star alone. And by subtracting those two, you get the spectrum of the planet. But it's really getting precision spectroscopy and then looking for the fingerprints in the spectrum, the absorption lines that correspond to these biomarkers, these really important fingerprints such as methane, oxygen, carbon dioxide, and to really have a sense of what is in this atmosphere. And this is an area of really active and exciting research by astronomers. If you talk to graduate students about what they're really excited about working on, it's exoplanets.
Great. I'd like to invite people to ask questions of the panel. If you have questions you'd like addressed, yeah.
So you're talking about methane and water and maybe other carbon-based molecules so that life can consume them. But didn't we just discover, I don't know, 5 years ago that some bacteria on Earth actually consume electrons directly and they form biocables? University of Southern California, as far as I know, they discovered such bacteria. So wouldn't that mean that maybe life exists on a gas planet with ionic atmosphere?
So the question is that, let me just repeat because not everybody can hear all the questions. So the question is about the possibility of life that's constructed around another form of biochemistry other than carbon chemistry, if I can generalize your question.
Oh, it's hard. Well, I guess personally what I tend to focus on is life where you've got liquid water as a solvent. You're using iron or something as a source of electrons, maybe hydrogen gas as a source of electrons in water. When you get to stuff that's more, we have plenty of really exotic life we found on Earth, but when you get to get more exotic than what we found on Earth, it's kind of hard because it's harder to test it, to see whether it's something we really expect to find or not. An enormous amount of extreme life on Earth as it is.
I think one thing you might argue is astronomy is simple, and yet we've been astounded by the complexity of the other systems we find. And biology is complicated, and you can extrapolate from that and figure that things are going to be different and more complicated elsewhere as well. Anita?
I think also what we've learned in looking at other planetary systems is nature is way more clever than we are and has come up with more variety. So yes, it's very possible there's life out there that runs by a different mechanism. But we don't know what it is, so we can't study it because our imaginations aren't good enough yet.
Yeah. I would add that if there is elsewhere life based on another biochemistry, it's going to be very hard for us to validate this as life.
Yeah, over there.
So you all have mentioned Europa, and I'd love to hear more about what you think the importance of the mission to Europa is going to be from NASA, but also just a few years ago, NASA wasn't going to go to Europa, and they changed their mind. Yeah. And I'm curious to know if you could explain that and if the Institute for Geophysics had something to do with it.
Oh, I cannot explain why they did change their mind, but I can actually try to tell you briefly the story. But a mission to Europa was actually a project that dates back to, after the Galileo mission that arrived in the Jupiter system by the end of the 90s, right after that, given the results we had from this mission, the planetary community wanted to go back, especially to Europa, because this Galileo mission proved that there is a big ocean beneath the ice at Europa. And from the beginning of from 2000, or maybe from 99 to today, there have been maybe at least three different mission projects to go to Europa. And some of them were a collaboration between NASA and ESA, the European Space Agency. And the issue was simply money, especially because in the US, when you fund a mission, when you fund a spacecraft, once the mission is kind of decided, you still have the risk year after year, government after government, that the politics do not want to fund the mission more, so they stop. And that happens with Europa. So today, we are at this point where the Congress, the US Congress, really wants a mission to Europa. And 1.5 years ago, they decided to launch this call for opportunity to have to ask the planetary community to propose some instruments to study Europa and to put them on a spacecraft. This spacecraft has no name yet. It's the NASA's Europa mission. But so far, it's going pretty good, but it's a NASA mission. Maybe a European payload is going to be on there, maybe. So far, so good. The politics they like Europa right now, and we'll see maybe in 5 or 10 years.
Yeah.
Once they build a giant Magellan telescope, will they be able to do spectroscopic analysis on like an individual exoplanet?
So with the next generation of large telescopes, will we be able to do spectroscopic analysis on individual large planets?
So there's two ways that this will be approached. One of them is using adaptive optics to separate the light of the star from the light of the planet and get spectra. And yes, we will be able to do that. There's a handful of planets, of giant planets so far, that this has been done with using adaptive optics on 8 to 10 meter telescopes. The other two techniques use either a planet that goes behind the star, because the planet is moving in the same plane as the star as seen from Earth, and then you take exposures with or without the planet there, or you get very precise spectroscopy of the whole system, and then you use the motion of the planet to be able to look for lines that move as the planet goes. But the really fundamental thing, I think, is that we are moving from the era. 20 years ago, the question was, are there planets around other stars? How common are they? And astronomers have done a really great job with that. We know planets are very, very common, and Earth mass planets are common. And now we're really moving into the realm where this spectroscopy that you asked about will really give us much more information about the properties of planets and a greater physical insight into what's happening on exoplanets.
Yeah.
Hello, I'm Janai from Istanbul. So I'm a basic person, right? So I'm seeing this brilliant, curious minds in front of me, and I thank you for that. My question is more about how we can make it more like a collaborative practice, because you are innovating stuff and we are the audience all the time. Is there a learning that you are figuring out, a philosophy, a practice, a methodology of innovation, that we move from being the audience only so that we can start also becoming a part of what you're doing, maybe?
Yeah, I can answer that.
So, go
Yeah,
ahead.
that actually is happening in the field of astronomy right now. There's a program called Universe Zoo, which is Universe Zoo. It's done used in the field of galaxies. It's used in the field of exoplanets. It's used in various things where people take large data sets that it would be almost impossible for us to go search through as astronomers, but put them out there and basically let people look for certain things in them, and you use training images or whatever, and then people will go ahead and mark what they see. So for instance, NASA recently had this mission, still flying, called the Kepler mission, which was looking for planets moving in front of their host stars. And there are Universe Zoo parts of the Kepler mission now where the public is going out and looking at some of the data and finding cases where they see a transit of something going through. And they have found planets that were not picked up by the people who were part of the Kepler mission, because people have an interest, and the public is funding these missions. It's very important to keep the public involved.
Right. I think I would also add to that we're also pushing the edges of technology. So we're trying new things in new ways, combining technology in new ways, and those things can be brought out into the public sphere to be applied in other areas as well over time. And at the same time, we're changing the worldview of everyone. When you know that there are other planets around other stars, it changes your picture of your own existence and where you live. And that's something that we try to share with everyone, what we know as quickly as we know it, to expand people's horizons and people's view of our own place in the universe.
Sure. The first time I ever encountered the idea that I know that someone suggested the idea that we could look for life on other planets by looking for signatures in the atmosphere rather than sending probes down to the surface was James Lovelock's suggestion. And part of that idea is that life can't be sparse on a planet. That when life evolves, either it takes over the surface and begins to control the content of the atmosphere and helps sustain the existence of life, or that if it isn't able to do that, after a while it goes extinct. it sounds like, is this now what people doing these searches believe, that planets will either be covered with life sufficient to change their atmospheres, or they won't have life at all? Is that the hypothesis behind these searches?
You know, when you say planets are going to be covered with life or no life at all, well,
life to change the atmosphere.
or enough life to change the atmosphere, that's going to be the easiest to detect. If there's enough life around an extrasolar planet to change the atmosphere, that's what we're probably going to require in order to detect it. But in general, I'd say I think it's very possible to have life without having enough of it to change the atmosphere. And I think of something like Mars, which had substantial liquid water on the surface 3.5 billion years ago. The water's largely, or the liquid water's largely gone from the surface now, but something like Mars could potentially have life still lurking a few kilometers below the surface, because once life gets started, it's pretty darn hard to kill it. That's one thing that we've learned on Earth. And there still could be, microbes living a few kilometers below the surface of Mars. The reason we know that is looking at the deep subsurface of Earth. But that would be life at a level which is not enough to change an atmosphere, but that's going to be a lot harder to detect.
I guess I would add to that that you can imagine also local ecosystems. For example, the moon has craters with water ice in them at the poles, where they're constantly in shadow. And they're not liquid, so that's not really relevant to this context. But you could imagine a situation on a very different kind of planet, where there's a very specific part of the planet that's conducive to forming life, but it's not enough to change the ecosystem of the whole planet. So possibly is the answer.
Hi. Piggybacking somewhat off of the other question here, is obviously there's a lot to learn, but is there any undercurrent sort of in the overall, let's call it mission, of discovering all these planets seeking life, that if we identify the right characteristics or setup, that we would then eventually act to help sort of, for the lack of a better description, speed up the development of life so that it makes it much more applicable for human colonization or spreading our species? That would seem a tidbit presumptive on us, but nevertheless, is there any of that type of thinking that's blended into the scientific community, or are we not even to the point of even considering that?
Well, I would say no, because before to act on something, to change something, we need to understand this thing, and we need to understand the consequences of what we are doing. And because we do not know how life appears and what are the different processing that are leading to life, there is nothing in the planetary community that would actually try to make life elsewhere or to boost life elsewhere. We don't understand that enough.
Hello, also a basic person from Panama. Basic question. What would you expect to find? I would like to hear each of your opinion. Once these new missions launch, the James Webb Telescope, the one in Chile, what's your dream discovery?
I guess I'll start as we go down the table. I guess my dream discovery is to be able to take a spectrum of a planet around another star and see clear signatures for the existence of significant life like the life we know here. So that we're still working on exactly what that would look like, even, much less being able to detect it. But if we could see that, that would be tremendously exciting.
Oh, this is interesting, because you're an astronomer, I'm a biologist, and the dream discovery is pretty much that's it. I want to see spectroscopic evidence that an extrasolar planet has an atmosphere which either is similar to Earth's now or similar to Earth's atmosphere at some point in the past after life first evolved on Earth almost 4 billion years ago. So spectrum of atmosphere, evidence of life, biosignature. That's my dream, yeah.
Well, I don't have any specific discovery in mind, but what I love in our fields, and what I would want our fields to show for the future, as we are showing right now, is how much space and planetary bodies in space, how much the diversity of them are high, either in terms of, and for me, in terms of landscapes or in terms of geophysics. You know, from Pluto and from the last New Horizon mission, you know that Pluto is finally a world that is way different that we could have expected, and way more interesting that we could have expected. And that's the same for life. I mean, if this, what I would want is to see that this principle of diversity in space still applies for the next generation, so that our discovery will show that there is full of unexpected things everywhere, and also for life. So.
Yeah, I agree with the speakers that I think the thing I'm looking forward to is proving there is life out there. But I want to take it the step further that Cyril wants to take it. I want to see, once you know how to identify life, what different conditions can you get life to form under? What different kinds of planets can you get life to form under? How common is life in the universe? And I think that's the holy grail.
I agree with all the speakers. All of this is my dream, but let me make a specific case of that dream. What Dan said about a spectrum of an exoplanet that has clear signatures of life. As long as we're dreaming, let's make it very close to Earth, and then let's imagine that it captivates our society, and that we use this to advance humankind to send a probe to that planet. And it'll take a very long time. It'll take developments in propulsion technology. It'll take developments in communications technology. But imagine that we have a very clear target that we're sending a probe to, much like the first probes that went to places like Mars and Venus and Jupiter. That's breaking out of the solar system with a probe.
Thanks.
Hi, hello. I'm Cullen. I'm also a basic person from Dallas. Just joined the bandwagon on that. Being a fan of your field and not being involved at all since I was a kid, I just feel like with all the technology and the research we're doing, I'm optimistically feeling like we're really close to finding like that microbe, you know, in water or something like that on another planet. But then I think, well, if we did, my question is, what do you think would happen to the industry in the field? Would it be just like, great, go find more? Or do you think there'd be a shift, you know, in interest, funding, or how, you know, where you're all looking? I'm just curious. Have y'all thought about that? As like, oh, if we do find that piece of life, what's going to happen next?
So the question is, if we do discover life on another planet, how would that affect the field? How would that change the direction of our research?
I think a lot would depend on where that life is. Is it close enough to even think about getting a spacecraft there, or do we try to come up with other techniques for looking at it? Because, I mean, if it's halfway across our galaxy, well, we can say it's very nice and we're going to learn from it, but we can't get there. But if it's the next star over, well, then we can try to work on the technology that would get us there and keeping people alive in space and all this. And I think there would be a big push to do something like that. But I would not stop all the other research, because I think it would just spur people on to wanting to know more about what else is out there.
I think one thing that's interesting to think about here is we're pushing up to cathedral scales in terms of the time it takes to do things. So the recent fascinating news about the discovery of gravitational waves by the LIGO experiment, that was a 35-year project. The Viking landers on Mars, until the earliest we could possibly get to Europa and detect life, is 60 years. And the detection from the first detection of exoplanets to this kind of spectroscopy we're talking about is, again, a 30 to 40-year timescale. So it's fascinating that society is taking on these substantial projects of discovery and supporting this kind of endeavor that unfolds over decades, and that all of us are part of, and we're of course very involved, but that the public is actually interested enough to see these things through. It's really fascinating to me, that aspect of it. Yeah.
Say you discovered life in a planet that is, 100,000 or a million light years away. Would you imagine what life would be now, because that was like a million years in the past? And what impact would that have?
So the question is, because if you actually make a discovery in a planet that's very far away, 100,000 light years or a million light years away, you're looking at the light arriving at you from that time in the past, and what would we imagine had happened in the ensuing time? So what's the contemporary state there?
Dan, I can try that. I mean, of course, a million years is a fairly short time in terms of the overall lifetime of the universe, on the order of, 13, 14 billion years. So I don't think it would impact our conclusions that much. But your question does raise a really important issue outside of this particular panel, and that is a lot of studies in astronomy today, particularly cosmological studies, are based on using that time travel of light to look back into other eras of the universe. So it has the biggest impact on studies of galaxies, where we look at light that's traveled to us for a few billion years, or we're up to looking at galaxies where the light has been traveling to us for 95% of the age of the universe. So we can't see planets, of course, in those galaxies. We can't see individual stars, but we have learned a tremendous amount about how the universe has evolved by using exactly the phenomena that you point out, that travel time of light. And that is one of the other most exciting areas of astronomy, is using that look-back time to try to see the first stars. And what were the first stars in the universe like?
Yeah.
Hey, oh.
Sorry. You want to hear first here and then back there?
Okay. Lost my train of thought. This is kind of a bit of paranoia that I have, but once you find this life and want to study it and bring it back here, how do we know it doesn't go out of control and kill mankind? I mean, because that's what's going to happen.
Oh, God.
I mean, they're going to bring it back. Well, they're going to bring it back, not that it's going to kill mankind, but...
I missed that movie.
Oh, yeah, oh, God. I think you just have to assume the worst and treat everything carefully until you understand what's going on. That's, yeah. I guess I'm not as paranoid as you are, but I'd be more optimistic that it's not going to cause problems, but we work under the assumption that things need to be isolated till they're understood.
And we did when the first moon rocks came back. They were quarantined, as were the astronauts when they first were in space, because we didn't know. And we are pretty careful about it. There is actually a NASA person whose job title is Planetary Protection Scientist.
Probably more concerned about us contaminating them than us.
It's both ways.
It works both ways, yeah.
So I would say the first question we are asking to us is not how we could protect ourselves from life, but it's now what we are doing. It's what we call planetary protection, is how we could protect other worlds from us. When we go to Mars, when we go to Europa, and when we land some craft on those worlds, there is a lot of procedures to try to make that those craft do not, import to those worlds some Earth lives. So that's the first question we ask first.
You all seem so passionate about what you do, and it's just so beautiful to see. Do you have graduate students, and we're talking about such a scientific problem, getting students into science and math. Do you have the graduate students to be here the 30 and 40 years after now?
You say we're passionate, but compared to the graduate students, we're actually depressive. I mean, the graduate students are amazing. And this field in particular has exploded in the last 20 years, and they're all over it, and they're just a thrill to watch and a thrill to work with. It's just an amazing thing.
It's true.
Just to go back to what you said, are you guys concerned some private companies already organized to study the possibility of mining other planets? And if you are, what do you think we should do about that?
I think it's probably realistic to think that there are companies who have in the back of their minds that they're going to mine certainly asteroids for materials to be able to go on. But it's really not an easy problem. Even NASA, who's been in space a long time, can't necessarily assure any mission that goes out of the near vicinity of our Earth is going to work. And so, I mean, we're not really worried about it. There are treaties in places that control what can be done. And I think some of us as scientists would welcome having additional resources from these private companies to actually go and study things. You can't mine something until you understand it. And that's to our advantage.
Yes, I had a question about the Search for Extraterrestrial Intelligence project that I remember from a long time ago. Does anybody know what the status is on that, and does it have any impact on what you're doing?
So actually, I'm surprised that it took until this far into the discussion for the subject to come up. Thank you. So the question is, how does what we're doing in the search for extraterrestrial life relate to the search for extraterrestrial intelligence?
There is a program, it has been called SETI in the past. Now, some of our congressmen have thought it's silly to go searching for extraterrestrial life. So it's moved more into the private realm. Very little government funding in it, but there is still a very active program of radio astronomy looking for signals from other planets, and they're utilizing the fact that we know now where some of these planets are to actually target those planets and see if you see any indication that there's intelligent life out there. One of the things we have to remember, though, when you start talking about looking for radio signals, we've only been putting out radio signals for the last, 200 years? And it's sort of been random going out. We're not sending out messages in any coherent ways. And actually, we're going a lot towards cable right now. So maybe we're going radio quiet to some extent. So it may be that you have to catch exactly the right moment. And that makes it very, very difficult.
There is one new idea in SETI that I've learned about recently. And in some ways, it follows the analogy of people taking pictures of people taking pictures. And that is when we use telescopes like the Giant Magellan Telescope, we send powerful lasers up into the atmosphere to do adaptive optics. And we tune those lasers to the wavelength of sodium, because there's sodium in the upper atmosphere that we excite, and we create an artificial star in the upper atmosphere. So you could imagine there might be astronomers on another planet orbiting another star that are also using the same technique. And if they were pointing their sodium laser looking at our solar system, we would see a flash from that solar system at the line of sodium. So it's people, thinking about how what we're doing, if other societies were doing those in space, that we could observe that. And the reason that this is of interest is it's a completely different technique than the radio. It would require the planet to have an atmosphere that also has sodium in it, and for them to have discovered adaptive optics.
Only.
It's related to this question, really. If those intelligent life forms are really intelligent, would they want to be discovered?
Well, how do we feel about it? Some of us on this planet have a large need for attention as we and others of us prefer to be more private.
It's hard to say, because there's always the fear that it will bring them here. For all we know, they've been here already. We're the experiment being run right now. But, I mean, it's really difficult to say if we knew there was another civilization out there, would we want to go radio quiet just to be careful? I don't know. I mean, some of us are curious enough, we just want to meet them.
I want to thank you guys for having this panel. It's been amazing. But I kind of want to ask a fun question. And you kind of were saying, when was they come up? But the alien megastructures found on the star. Not just proposed. I know it's highly speculative, but we have a comet specialist here. Just what are your thoughts on what was found on the irregular readings from, I can't repeat the name of the star because it's just a bunch of numbers.
That was anomalous reading from, I think it was from the Kepler project?
Yeah, from Kepler.
I'm not sure I know what we're referring to, so.
It's either a cluster of comets or a Dyson sphere or something is my recollection.
Bill, do you know?
Yeah.
This is another person from the department, my husband, Bill Cochran.
This is just a
who's an
fun
expert
question.
in-
The suggestion was that there were irregularities in the light output from the star that you guys usually.
okay, so
but
a
that
cloud
these-
of
but that
comets.
it said, no, that suggested that the only thing that this could be would be a Dyson sphere, an advanced civilization capturing the energy of their central star for whatever cool reason they thought they wanted to do it. This was the only thing that could explain potentially these irregularities.
That's just because we're not very creative. Nature is very creative. And sometimes the signals that we see that we think we understand one way turn out to be something totally different.
I'll just ask one more quick question. It bears a little bit on this, but because we have a mechanism, or we think we have a mechanism for how simple forms of life change to more complex forms, evolution, but we have no mechanism for how inanimate, inorganic material becomes living, we tend to think that the origin of life is hard and the evolution of complex life will just progress naturally once something simple. But the history of life on Earth is mostly bacteria and algal mats. That's 90% of it. So does this mean that most of these planets, if they have life, are going to have bacteria and algal mats? Not that there's anything wrong with bacteria and algal mats. They're pretty cool. But there may not be that much intelligent life, even if the universe is full of life.
Well, the thing we learned from our Earth, there's a period of time called the late heavy bombardment where there was a lot of impacts which kept frustrating life, and yet life just kept coming. Life is not hard. Life is actually quite easy. Getting to complex life may be hard. We don't know.
Do you want to say something about that?
That's why, yeah, getting to complex life, that's one thing detecting a biosignature in an extrasolar planet will go a long way toward answering that question. Is complex life easy or is complex life hard? And if your definition of complex is photosynthesis, that's a question that might be answered in a modest number of years now.
Right. I mean, I guess that's true that this is an issue, but I think also we're at a point where we now know that there's a tremendous variety with the planets, as Anita was referring to, that there's a possibility that moons have life on them. There's the possibility of planets near very faint stars that are orbiting very close to the stars that have liquid water. So there are many, many other avenues for producing life in planetary systems than we have in our own solar system even. So yes, it may be difficult, but there are a lot of chances out there to get it done. I think we can probably have time for one more question if someone...
Hello, beyond basic down here. I wanted to ask you about Mars One, kind of the science community, about whether you think it's actually going to happen, whether they're going to run a reality TV show on Mars, whether any of the things they're promising are actually at all likely.
Some year.
Well, so the question is...
is Mars One, I suppose,
is Mars One
going to happen?
Okay, that's a topic. Well, Mars One, they have... So first, they succeeded to gather around them a very dynamic community, which is always very nice to see from our perspective, to see some people very excited about planetary exploration. So that's the first. The second is that I've never had, when I tried to look into details into the Mars One plan, and actually I think they have a talk here on Tuesday or something. And nothing convinced me in their plan that what they want to do could be done given their timeline. You know, especially when we're working in the field. I mean, we are making science. We are also building instruments and participate in spacecraft elaboration. You know, with NASA and other space agencies. So we know what it takes to just launch a tin can. You know, without any humans around Mars. We know how much it takes and how long is it and how hard is it. And based on this experience, I don't see any convincing arguments in Mars One's plan to achieve their goal the way they want to achieve it.
I want to thank all of you for coming today. It's been great having a chance to talk to you and interact with you about all of these interesting questions. Here at UT, in various fields, we're working towards making these things a reality along with our many colleagues throughout the field. And I guess we can change our motto now to what starts here changes the universe. So thank you all for coming.